Okay, here's some more problems for you. Sample problems worked out just like the kind that will be on the test. What is the wavelength of a photon that has the same momentum as an electron moving with a speed of 1400 meters per second? You'll recall I said that photons have properties that make them look like particles and properties that make them look like waves. Well, one of their particle-like properties is that they have momentum. You remember from when we did collisions and conservation of momentum, that momentum is mass times velocity. Well, photons don't have any mass. But it turns out, nonetheless, they do have momentum that is given by a formula that here is the momentum of a photon. I don't have it written down on one line, but it's right there. Planck's constant divided by the wavelength. So the bigger the wavelength, the smaller the momentum of this photon. So it says I've got an electron traveling at a certain velocity, and I want to know the wavelength of a photon that has the same amount of momentum. You remember we talked about when photons strike electrons and knock the electrons out of an atom. Well, you have to have momentum conserved, so whatever the momentum before is going to have to be the momentum after. So I set the momentum of an electron equal to the momentum of a photon because that's what the problem said would happen. Well, for an electron, it's the mass of an electron times the velocity of an electron. And for the photon, it is h over lambda. And I plug the numbers in. There's mass for electron. There's the velocity of the electron. There's Planck's constant. All that leaves me is looking for lambda. I cross-multiplied and found out that it is 5.2 times 10 to the minus 7. That is 520 nanometers, which happens to be yellow light. So yellow light has the same momentum. One photon of it has the same momentum as an electron traveling at 1400 meters per second. How odd is that? Number 7. A photographer's light meter uses a photocell to measure the light falling on the subject to be photographed. Well, that's nice. What should be the work function of the cathode to be if the photocell is to be sensitive to red light of wavelength 689 nanometers? I may have kind of convoluted that. And then it says express that in electron volts. Well, what it's asking is, don't worry about that whole cathode thing. That is something that will emit electrons. It says that I have red light that is 680 nanometers long, and it asked me to calculate the work function. Well, again, from Einstein's photoelectric formula, that's the photoelectric formula. But since we have wavelength, I'm going to substitute, instead of F, I'm going to use C over lambda. Here I just plug in the numbers. And all this works out to an energy per photon of 2.93 times 10 to the, that actually is supposed to say minus, and we'll fix it right now. 2.93 times 10 to the minus 19 joules. But the problem asked me to express it in electron volts. You'll recall that an electron volt is just a very tiny little unit of energy. It's so tiny that 1 electron volt only has 1.6 times 10 to the minus 19 joules worth of energy in it. So I cancel, I've got joules upstairs and joules downstairs, so they go away. So all I have is EV, electron volts, and it's 2.93 divided by 1.6, works out to 1.83 electron volts. You will find that when you study atomic stuff, that to have photons and electrons that have energy in the 2 or 3 or 10 or 20 electron volt range is very common. That's the reason why we use that. Okay, let's do number 8. See how we like it. A laser produces a 500 milliwatt beam of light consisting of photons with wavelengths 632.8 nanometers. How many photons are emitted by the laser each second? Well, this is a problem we've done a number of times. The first thing we have to do is figure out the energy associated with each photon made by this laser. Photoelectric law, instead of using frequency, since I have wavelength, I use C over lambda, plug and chug, and then boom. Each photon has 3.14 times 10 to the minus 19 joules worth of energy associated with it. Now I have to figure out the total power generated by this laser. It is 5 milliwatts. So power, you'll recall from other problems, is energy over time. 5 milliwatts is energy over 1 second. It says how many photons per second. So that makes the total energy 5 times 10 to the minus 3. So as we've done before, this is the total energy. This is the energy per photon. And so if I take the total energy divided by the energy per photon, I end up getting the number of photons. This laser produces 1.59 times 10 to the 16 photons every second. Now, that was the A part of the problem. The B part says the laser beam strikes a black surface and is absorbed. What is the change in the momentum of each photon that is absorbed? Okay, you can imagine that like it's the old collision problem we did where there's the stationary skater and the moving skater, and when they crash together, momentum is conserved. Actually, perhaps a better example would be when we did two pool balls, and after the collision, the one that was rolling before the collision stopped. Well, that's what's going on here. When there is something that is black in color, it means that the photons that are hitting it are absorbed. So that means they give up their momentum. So here I have the formula for the momentum of a photon. Momentum of a photon is Planck's constant over the wavelength of the photon. So I plug in Planck's constant, I plug in the wavelength that it gave us, and when I plug and chug, I get that the momentum associated with one photon is 1.05 times 10 to the minus 27. That's how much it had coming in. Afterwards, it wasn't moving, so it gave up that much momentum right there. All right, the C part of the question is, what force does the laser beam exert on the black surface? Well, the momentum that the momentum is the amount of momentum per photon times that's right there, momentum per photon times the total number of photons will give the total momentum. So there's the total photon count, there's the amount of momentum per photon, and when you work it all out, this is the total momentum that it exerts on the wall. Now, the reason I paused in the middle of that is it just occurred to me, it doesn't ask what the momentum is, total momentum, it asks what the force is. However, you know how to solve that problem because that's last semester stuff. Change of momentum is impulse. You know what? I'm not going to tell you. You need to work those out by yourself. 2 more problems, and I'll call it a night. This branches out into de Broglie waves. Remember that once we realized that things that we thought were waves could act like particles, it occurred to Louise de Broglie that things that we think of as particles might have waves, and indeed they do. Wavelengths, that is, might behave like waves. So it says I've got a particle. I'm sorry, let me give you the de Broglie equation. The wavelength of a particle is h over its momentum, the particle's momentum, and momentum is just mass times velocity. Rearranging this part of the formula and this part of the formula, I'm asked a question about velocity, so I just cross-multiplied and got that the velocity is equal to Planck's constant divided by the mass times the wavelength. A particle with a mass of 6.69 times 10 to the minus 27 kilograms has a wavelength of 7.62 picometers. Pico is 10 to the minus 12. What is the particle's speed? All right, so once I isolated for this variable, I plug numbers into my equation. There's Planck's constant, there's the mass, there's the wavelength, and the next thing you know, I got the velocity is 1.3 times 10 to the 4 meters per second. That's 13,000 meters a second. That's moving on. That tells you how to use the de Broglie wave equation. And then lastly is this one, number 10, uncertainty principle. That's what we talked about today. The uncertainty in position of a proton is confined to the nucleus of an atom. A proton that is confined to the nucleus of an atom is roughly the diameter of the nucleus. If the diameter is 7.5 times 10 to the minus 15 meters, what is the uncertainty in the proton's momentum? Well, the uncertainty principle, uncertainty in momentum times uncertainty in position has got to be greater than h divided by 2 pi. And again, it gave us everything except the uncertainty and momentum, so I just cross multiplied. So now all I got to do is plug numbers into that equation. Here's h on the top, there's 2 pi, there is my delta x, and when I solve it, it is 1.41 times 10 to the minus 20 units of momentum, kilogram meters per second, which is a fairly small ambiguity in its momentum, but that is because we live in a world where Planck's constant is a very small number. I hope working those out helped. We'll do some more in class tomorrow. Thanks.